Welcome to the training module on testing and commissioning electrical grid, focusing specifically on the AC distribution panel, or ACDB. This session is part of our ongoing electrical grid training series for 2026, designed to equip you with the essential skills and knowledge to effectively test and commission these critical components. Let's dive into the details and ensure a thorough understanding of ACDB operations and safety procedures. Here we have the reference framework for testing and commissioning electrical grids. This slide outlines the key organizations and standards that form the foundation for our commissioning manual and test scripts. The most important point here is that we rely heavily on established bodies like the IEC, IEEE, ASTM, NEMA, ANSI, SIGER, ICA, and KEMA, each bringing their own expertise in electrical standards and testing. It's critical to apply the most stringent approved requirement whenever there are differences between project specifications, manufacturer instructions, or standards. Also, it's essential to document which reference was used on the test sheet so that anyone reviewing the results later can understand why a particular outcome was accepted. This ensures clarity and accountability throughout the commissioning process. Here we have the ACDB panels, MCB and MCCB test schematic, which serves as a crucial reference for testing and commissioning electrical grids. This schematic details procedures for verifying breaker continuity, conducting MCB and MCCB trip tests, as well as performing primary and secondary current injections. Additionally, it includes guidance on trip time acceptance to ensure breakers operate within specified parameters. This document is part of our commissioning manual number 11-1 and forms the backbone of our quality assurance during the commissioning phase. Now let's go through the testing and commissioning process for ACDB panels, focusing on MCB and MCCB tests. These tests ensure that the miniature and molded case circuit breakers function reliably by checking continuity, pickup and trip operation, injected current, trip time, and restoration. First, we rely on key references such as the approved ACDB schematic, panel schedules, manufacturer manuals, protection settings, and test sheets. The necessary instruments include primary and secondary current injection kits, calibrated multimeters, continuity testers, clamp meters, insulated leads, and essential safety equipment like PP, barricades, and safety tags. Our step-by-step script starts with confirming all documentation and breaker details, followed by applying lockout-tagout procedures and verifying safe isolation. We then conduct a thorough mechanical and visual inspection, checking labels, breaker positions, torque marks, terminals, shrouds, arc chutes, and panel cleanliness. The continuity check comes next, ensuring the breaker poles are correctly connected when closed and open when switched off. For trip testing, we connect the injection kit to the MCB, injecting current per the breaker's rating and recording trip currents and times for each pole. Similarly, for MCCBs, we perform primary injection tests and document the time current response according to approved multiples of rated current. We compare the recorded trip times against manufacturer curves and project acceptance limits, investigating any anomalies such as delayed or nuisance trips. Finally, we restore breakers to normal positions, remove temporary connections, reset alarms, and document the final condition of the ACDB panel. Acceptance criteria require that breaker continuity, mechanical condition, injected current, and trip times all comply with approved settings and manufacturer specifications, with no signs of overheating, damage, or unsafe conditions. As evidence, we compile MCB/MCCB test sheets, injection readings, trip time tables, reference documents, instrument calibration certificates, photos, punch list closures, and witness sign-offs. Importantly, before releasing the panel to normal service, a commissioning or operations witness must confirm isolation, injection setup, test results, restoration, panel covers, and overall ACDB condition at the hold point. This ensures safety and reliability for the electrical grid operation. Here we have the schematic for ACDB auxiliary relays and timers, which serves as a key reference during testing and commissioning of the electrical grid. This diagram provides detailed information on the DC supervision relay, including how auxiliary relay pickup and dropout functions operate. It also covers contact timing, coil resistance measurements, and contact continuity checks, ensuring each component works reliably. This document is an essential part of the commissioning manual, helping us verify and validate the proper functioning of the system before it goes live. This slide covers the testing and commissioning process for ACDB panels, specifically focusing on auxiliary relays and timers. The key here is to verify several critical parameters including pickup voltage, dropout voltage, reset ratio, timing, coil resistance, and contact integrity to ensure proper functioning. We start by reviewing all relevant documentation, such as the approved control schematic, relay datasheets, and test forms. Then, using instruments like a secondary injection test kit, calibrated multimeter, and continuity tester, we follow a step-by-step testing script. This includes safely isolating the relay circuit, connecting test equipment according to schematic terminals, gradually increasing voltage to record pickup points, and then decreasing it to record dropout points. Further, we calculate the reset ratio and measure coil resistance to compare with baseline values. We also check contact continuity and resistance for both normally open and normally closed contacts under specified conditions. After completing these tests, the relay is reinstalled, wiring restored, and the circuit verification ensures alarms and indications respond correctly before returning to normal service. The acceptance criteria demand that all measured values meet approved settings or manufacturer limits, and the relay operates reliably without malfunctions. Finally, the evidence package includes detailed test sheets, timing records, calibration certificates, and photographic proof of restored wiring, with a hold point where a witness confirms correct relay insertion, link removal, and absence of abnormalities before proceeding. This thorough approach guarantees the safety and reliability of the electrical grid's control system. Here we have the ACDB panel's other component test schematic, which serves as a crucial reference during the testing and commissioning of the electrical grid. This schematic covers key areas such as busbar insulation resistance and busbar phasing, ensuring that our primary conductors are properly isolated and phased. It also includes tests for current transformers and voltage transformers, protection relays, metering devices, as well as cable and function test interfaces. All these tests are essential to certify the proper operation and safety of the ACDB panels before they go live. This information is detailed in the commissioning manual number 11-3, which guides us through each step meticulously. On this slide, we focus on the testing and commissioning process for ACDB panels, specifically other component tests. The key activities begin with verifying that the ACDB is fully isolated from all power sources, backfeeds, capacitors, and connected loads before conducting busbar insulation testing. Next, we review the busbar arrangement, neutral and earth bars, CT/VT links, surge protection, meters, relays, feeders, and test boundaries to ensure everything is accounted for. A thorough visual inspection follows, checking busbar supports, insulation barriers, clearances, covers, cable glandings, labels, torque marks, and cleanliness. Then, insulation resistance tests are performed phase-to-ground and phase-to-phase, using approved test voltages, with careful recording of ambient conditions and proper discharge of busbars after testing. We also conduct busbar phasing and continuity checks from the incomer to the bus section and outgoing terminals, cross-checking that related CTs, VTs, protection relays, metering, and cable test packages are complete or have documented open dependencies. After testing, all links, barriers, and covers are restored, ensuring no forgotten temporary connections, missing terminal screws, or exposed live parts remain. Acceptance criteria require busbar insulation values to comply with project and manufacturer standards, and for phasing to be correct with all barriers and labels in place. Linked component test dependencies must either be closed or formally controlled as punch items. We document results thoroughly with inspection checklists, insulation tables, phasing records, dependency lists, photos, calibration certificates, punch registers, and witness sign-offs. Finally, a critical hold point demands electrical lead and operations witnesses confirm IR discharge, correct phase reference, restored barriers, and the absence of any unapproved energized condition before moving on to functional tests. Here we have the schematic for the ACDB LV automatic transfer switching scheme, which is essential for ensuring a reliable power supply. This diagram provides a clear reference for the dual incomer setup, including the bus section breaker and the interlocking of Q1, Q2, and Q3 breakers. It also details the critical functions such as source loss transfer, return transfer, and protection trip blocking logic, all of which work together to maintain system stability and prevent faults. This information is drawn from commissioning manual number 11-4 and is vital during the testing and commissioning phases of the electrical grid. On this slide, we focus on the testing and commissioning of the ACDB automatic transfer switching scheme. The main goal here is to verify the proper functioning of the transfer switching logic, including interlocks, source loss behavior, return sequences, and trip blocking protection. We start by confirming the normal starting conditions, ensuring all incomers are closed as required and both power sources are available. Next, we review the ATS permissive logic, electrical and mechanical interlocks, timer settings, trip inputs, and selector positions to make sure everything is correctly configured. The testing script guides us through simulating a loss or manual opening of incomer 1, verifying that Q1 trips and Q2 closes after the approved delay. Then, upon restoring incomer 1, we confirm that Q1 recloses and Q2 opens without any unintended paralleling. We also simulate protection trips and check that breakers remain blocked or open as per the cause and effect logic. This sequence is repeated for incomer 2 and Q3 to ensure consistent behavior. We verify local indications, remote status updates, alarms, and all event logs to ensure everything matches expected outcomes. Finally, all controls, timers, and alarms are returned to their approved normal state, and the results are thoroughly documented. The acceptance criteria emphasize that the transfer and retransfer sequences must occur in the correct order and delay, with interlocks preventing unsafe conditions and all indications and alarms functioning properly. An important hold point requires a witness to confirm that no unintended paralleling occurred, no source was left disabled, and the ACDB is fully restored to automatic operation before final sign-off. This detailed process ensures a safe and reliable automatic transfer switching system. Here we have the ACDB ATS phase sequence and phasing schematic, which is essential for testing and commissioning the electrical grid. This schematic serves as a reference for the phasing test, helping us verify the correct phase sequence using phase sequence meters. It also allows for voltage comparison between Busbar 1 and Busbar 2, ensuring proper alignment. Additionally, it assists in confirming the bus section open status. This step is crucial to guarantee safe and reliable operation of the electrical system. All these procedures are detailed in the commissioning manual number 11-5. Here we have a detailed phase sequence and phasing test script for the ACDB ATS, which is a crucial step in testing and commissioning the electrical grid. The primary goal here is the verification of ACDB source phasing and phase sequence before any automatic transfer, bus section closing, or load energization occurs. To accomplish this, we rely on several references including the approved single-line diagram, phase reference drawings, ATS schematic, and voltage level records. The necessary equipment involves calibrated voltmeters, phase sequence meters, multimeters, a 3-phase test supply, insulated leads, along with proper PP and barricades for safety. The procedure is broken down into clear, step-by-step instructions. First, confirm the approved test window and safe conditions. Next, verify terminal identification on both bus bars to avoid any confusion during testing. Then, conduct voltage measurements between the bus bars, ensuring that same-phase voltages approach zero, while cross-phase voltages correspond to line voltage. Following these measurements, connect the phase sequence meters at both ends using the approved test supply. It's essential to confirm both ends show the same phase rotation with no reverse sequence before enabling any ATS transfer or closing logic. If any anomalies such as abnormal voltages, reversed phase sequences, missing neutral references, or inconsistent markings are detected, they must be thoroughly investigated before moving forward. Finally, remove test leads, restore covers, document the breaker and bus section status, and issue the phasing acceptance record. The test's acceptance criteria require correct phase identification, voltage readings, and rotation for both sources with no unsafe conditions or discrepancies remaining. All results and evidence, including test sheets, calibration certificates, photos, and witness sign-offs, form the final bundle needed for acceptance. Importantly, this process includes a hold point. Operations and commissioning must witness and confirm correct phase rotation and bus section status before any ATS energization, transfer testing, or final release can proceed, ensuring safety and reliability throughout the electrical grid commissioning.